should have been using Specs2.
Not Specs2, but maybe actually that thing is going to be useful. So I think this talk ties in pretty well with the end of last talk on how you do computations of like streaming financial data, for example. So Origami is a library for monadic folds in Scala. It looks a bit weird. What's a monadic fold? So that's what we're going to see. But first of all, thanks to Charles for coming up with the name Origami. So the previous name was not very sexy. This one is a lot better. In many situations, you have streaming elements, whether because they come from files or just because they don't fit in memory. So you have to just deal with them one by one. And I was playing 2 years ago with scalaz-stream, and scalaz-stream, when I first heard of it, had a great promise. I mean, it looked very interesting for me because basically scalaz-stream was saying, oh, you can take different computations you want to do on those streaming elements, and you just have to tag them together, and then you got your results in a very functional way. And I said, oh, that's great. No more for loops with fuzzy variables and all, just purely functional stuff. So I started playing with it, and well, it was not so easy at first. I had some issues with the API, I had some bugs, so I wrote a few blog posts on it. And what I was trying to do here was just to read a simple file, which had different sections with different headers and footers inside the file, where you could validate, for example, the number of lines in a given section. So I was just trying to validate my file and basically do maybe a simple transformation on the file and output it to a different file. It was pretty simple. But my main issue was not really the API or even the bugs. My main issue with this approach was that it was horribly slow. I mean, compared to just reading a file with scala.io.source and then reading the lines, having a bunch of variables to accumulate some state and then outputting the results, it was at least 10 times slower, really, really, really slow. So it was a big problem for me. Anyway, I stuck with scalaz-stream, and when I reworked the implementation of Specs2 1 year ago, and because when I'm reporting elements in Specs2, the results of your tests, you can report them either in an XML file for your CI server, for example, or you can report the results on the console or to an HTML file. And you don't want to have to do three passes over your data to do that. It's better if you can just do one pass and have 3 reporting being done at the same time. So I came up with this structure, something called a fold, and I found that this was pretty convenient because you can take different folds together and group them and just make one big fold that's going to do exactly what you want. So I was pretty happy with this, and I was so happy that I decided to talk to everyone about it at Lambda Jam and say, oh, that's great, you should use that. And then a few months ago, I discovered that I was not alone having this kind of idea of kind of encapsulating what's the essence of a fold into one data structure. I mean, this has been written quite a long time ago, 2008. But that's buried in Haskell world, so it's not very well known, but it's there. And more recently, you had, so that's a blog post from Conal Elliott. And the second one is a blog post from Ed Kmet, and it's actually a very long blog post, very in-depth about what is a fold and what you can do with it. So I encourage you to have a read and have a look at that. And what we can see here is that there's a fold-L library already in Haskell. So if you're using Haskell, it's fine. You have already lots of machinery to basically do computations on streaming elements. But you don't necessarily have the same equivalent thing in Scala. So I thought, oh, why not give it a go and try to see if I can use the same kind of thing in Scala. So my objectives here are to be able to reuse those computations. So if you write something that's going to do a checksum on a file, for example, you don't want to have to rewrite this basic computation over and over. If you're writing something like correlation, covariance, average, all the statistics, minimum, maximum, and you want this computation, you want to write it once and just being able to reuse it on any given stream. So that can be just a simple iterator, can be a scalaz-stream, can be an Akka stream, it can be a Java input stream, whatever is streaming data, you should be able to use this data as an input and reuse one of those prepackaged computation on top of this stream of elements. The second thing you want to do is to be able to group those computations together so that you can just, in one pass, do many of them at once. So you need some operators to be able to compose those computations together. But you also want this to be performant. So in particular, if we go back to my example with scalaz-stream, I might start with trying to read the file with scalaz-stream, do my computations. Oh, it's horribly slow. OK, I forget about scalaz-stream. I want to be able to use the exact same computations on a single, a very simple Scala iterator. Should be I shouldn't have to change too much code just to get the same effect. And the last point is safety, because when you are running computations, you might have exceptions, and you want your streaming and processing to be safe, especially in terms of resources. So if something blows up in the middle of you reading a file, you want to make sure that this file is going to be closed properly at the end. So let's have a look at this. But first, let's see what we usually do when we have to deal with streaming data and we have to add different computations on top of that using simple for loops. So in this example, I'm just trying to just count the number of lines, and I want to count, sum up the size of each line and get the final results of number of lines and the size of each line. So what you usually do in Scala in a for loop, you need to have two variables. Oh, that's ugly already. And then you mutate them here. So as you can see, your logic is already spread into two different places. So you cannot say, oh, I have a new component just counting lines, and I'm just adding this to my program. You have to take your component and split it in two parts. One part is here, one part is there. That's not very nice. And the situation is not very different if you use a more functional idiom, like using a for left, because you still have your logic being split into two places here, right? And in the more general case, your logic is split in three different places because you need some initialization, you need your accumulation here, and if you do something like an average, you need to finalize your last results. So basically, I have two components doing two different things here, and they are like spread out in three different places. So there's not much I can reuse here, and it's not very composable. Not nice. Another thing which is hard to do like this is to stop in the middle of your computation. So if you want to stop, if one condition becomes true, how do you do with the for each? So anyone who is thinking, I'm going to throw an exception, out. No exception. So there must be better ways, right, of stopping a computation like that. So we need to solve this problem as well. And the last problem we need to solve is we need to make sure that the source is going to be closed whatever happens, right? So if you write your program using a for loop, forgetting about closing the source, you're doing it wrong. You don't want this to happen. It's very important to close resources. So that's what the Origami library provides. It provides, yes, I wish I could do that. So it provides two abstractions. One to describe what is a fold, what does it mean to fold data, and another one is what is a foldable, what does it mean to be able to stream elements for something that's going to fold them. So the fold trait is something where you have a state, and that state can either be exposed to the client. We're going to see concrete examples of that. But it can also be hidden, and that can be useful because that means that your state can be actually pretty ugly if you want to. It can be mutable to make it fast or whatever, but you can encapsulate so that it's hidden from the client of your fold. For example, when we compute a checksum and we use a Java .message digest, this is a mutable object and we don't want to expose it at the end, so we just keep it internal. Then you have you need to initialize your state with the start value. This is the fold method. So the fold method is simply taking the existing state, the current element, returning a new state. And finally, sometimes you need to just finalize the value, make it a final useful value. And this is why you have the end method here. And so that's for the fold. And something that's foldable is just able to provide some elements of type A. That's the stream of elements. And given a fold, is going to return finally a B. That's the result of your computation. And all of this happen in a monadic context. It can happen in a context. So we'll see some examples of that. But that's what it means to be foldable. Well, let's see a very concrete example. I just want to be able to count the number of elements. So I'm creating a fold here that's just going to count the number of elements of type T, right? So this is a fold. The state is int. I'm just counting. The initial state is 0. Folding is just adding 1, and I'm not doing anything with the end value. There's no real monad here. That's the identity monad. There's no side effect. I'm not doing anything fancy. Everything is pure. It's all nice. And there are implicits so that the list is effectively a foldable M. So you can fold on a list. So when you run the count fold on the list, you get the number of elements. You get 3. So if you run that program, it's all sweet and easy. So now let's do a small tour of the library. So what has the library to offer in addition to those two abstractions? So as I said, one of the objectives of having a fold library is to be able to reuse stuff. So code it once, reuse it in many different contexts. So in the library, you will find things like, things to count elements, so count the number of elements, count all the elements satisfying a given predicate, count number of unique elements. Well, this one is a bit dangerous because it's using a hash set internally. So if you have too many distinct elements, it's going to eventually blow up. It's not very smart. You could make this smarter. You can check a predicate over any number of elements. You can do multiplications, addition over your elements. So all of these are instances of folds, right? Very simple folds, very simple state, doing what they have to do. And then if your data has an order, you can get the maximum, minimum, maximum by given attribute and things like that. You can also get the first n elements, the last n elements. You can get the number of times an element is changing its value, is flipping value. You can get the proportion of elements satisfying a given predicate. So, well, you're just limited by your imagination here. So there are a few statistical folds provided, but I guess you could add a lot more. So, for example, there's a question. You need the mic.
What happens if maximum doesn't get anything through the fold?
I think it returns an option. Okay, and there are some random stuff, and this one is actually, I find it interesting. So reservoir sampling is a method to return n elements from a stream so that each element from the stream has the same probability to end up in the final list. That's really cool. When I first heard about that, I didn't realize that it was even possible to get elements from a stream without knowing the full length of the stream, and eventually get a sub-list of this stream so that each element from the stream has the same probability to end up in the final result. I find this interesting. Then you have some checksums again, and that's it. So that's for the provided. So in the library, you have a few folds which have been created for you, but I guess you can come up with a lot more folds for your specific business. Now we need combinators. We need combinators to first create those folds from scratch or to combine them together. So in case you're wondering, what is this? It's actually the first thing which shows up when you go Google images combinators. So I guess that's like a huge comb is a combinator. And that's... yeah, that's in agriculture, they said it's a combinator. Well, I didn't see it that way. So one of the most important combinator in the library is the zip combinator. So this symbol here, you can also write zip instead of having an operator like that. But this one is really cool because this one allows you to take two independent folds, zip them together into one fold that's just going to do two computations at once over the stream of data. So if you want to count stuff and then also sum the elements in your stream, which is just a list here, you can just run the list over the new fold here, and you get the results. You can also use the map operation on the fold, and the map operation is going to take the last value that's being produced and transform it to something else. So in that case, we're computing the average, which is effectively using the number of elements and the sum. And if we run the average here, we get 2. So a bit of category theory moment. Oh, that's a functor. That means that there's this fold is a functor. It has a map operation. Okay, so how do you create folds? In the first example, I've showed you that you create a new trait, you give it a state, a fold, a start method, and so on. But sometimes your folds are very simple. You just need an initial value and the folding function, taking the previous state, the current element, returning a new state. So it's a bit like a fold left. So if you have something which looks like a fold left, the from fold left method is going to create a fold for you. If you have something where you can map each element to a monoid, like int, you will also get a fold with the from monoid map. That's another way to create a fold when the elements that you're projecting to are forming a monoid. Another way is to take an existing fold. So this one is an existing fold. It could be something else. But this fold is expecting some ints. But what you have is some elements of type T. So you can contra map, which is a fancy name for adapt, the input elements, change them to something else. In that case, I don't care what the input element is. I just put 1. So you can adapt existing folds, adapt the input of the fold to something which you want, whereas previously with the map method, we were changing the result of the fold. So contra map is adapting the input, map is adapting the output if you want. And in fancy terms, this makes it a contravariant functor, which means that the full thing is a profunctor. Ooh. I said it. Okay, so one other things which you can do, you can take a fold with the last 1,000 elements, and you can pipe it into another fold to compute the mean. So that's a pipe combinator. You can also compose 2 folds together. That means if you have a fold going from A to B, a fold going from B to C, you can make a fold going from A to C. And this one is going to compute all the different sums. It's a bit like a scan left on the collections, on the Scala collections, returning you all the successive sums when you sum stuff. And then you have this strange map flatten operation where you want to do some kind of side effect on the last element, and it's not quite a flat map because it doesn't have the signature of the flat map, so give it a fancy name like a map flatten. Okay, how do we do breaking out? You remember one of the issues we had was okay, I want to stop in the middle of the loop. How do we do it? So there are different ways to do it, and Arnold sent me a link to his library the other day showing me that Clojure is modeling things differently. So this is how I did it. I don't think that's really optimal, but this is how I did it. Actually, the full type for foldable M, which is something which you can fold, like a list, a scalaz-stream, an iterator, this has an additional method called foldMBreak, where if the fold that you're using, its state is either S or the same S, either it's left, either it's right, this indicates that we should stop computing stuff. So when I'm implementing this method, every time I see that I have a left value that's being returned, I know I can stop. If I have only right values being accumulated in my state, I know that I need to go on computing stuff. So that's one way to model this. But this way allows the following syntax, where you take a fold and you have this break when method where you pass in a predicate, and this says, okay, count stuff, you count stuff, but stop as soon as you have at least 10 elements, and that's it. So if you run that on a list, you will either get the size of the list if it's smaller than 10, or you get 10, because you cannot go further. Okay, now let's see a more complex example where we will have some side effects. So we are going to take the first examples where we had the for loop. Oh, yeah.
How do you know after the run break that it has broken? That's not probably right, but because it just returns.
Oh no, you don't know.
You don't know.
No.
There's no way to know. Okay.
No, you don't know. You would like to know? Yeah. Okay.
So Eric, when you've got one fold that's breaking early. Oh, I almost said breaking bad. When you've got one fold that's breaking early, yeah, and you use your combinators like zip, everything magically works like the other folds that need to go the full length still go the full length. And
I don't know. It's a good question.
Okay.
Yeah. I don't know. I'm not sure that's going to work.
So a use case would be like, I want to get the max and the min and calculate the difference. So I want to use the zip combinator between my max and my min.
Yeah, I don't think that's going to work, because when you zip the states, you're going to have the state of the zipped thing is going to be S1 just paired with S2. And it's not going to be something of the form S or S1 or S1.
Okay, opportunity for me to send you a pull request.
Yeah. But actually, I mean, this whole break thing might not be such a good idea anyway, because it's not very performant, because you're boxing value all the time. So it might not be the best thing to do if you want more performances anyway. So, yeah.
Okay, last comment. Yeah, you can get out of the boxing if you have a look at mine. You'll see.
Okay. Cool. I knew you had some more remarks, but that's good. That's good. Let's make it better. Okay. So let's go back to the first examples where we had the for loop. So we're reading lines from a file using Scala IO source. I'm creating a new fold, just going to accumulate the size of each line and accumulating that. So that's a fold. I'm creating it. I'm reusing the count fold coming from the library, and I'm just zipping the two to get a result, and then I can run it. So this is nice. That's basically rewriting the example we had with the for loop. And now I have two of my goals that I have reuse of one fold out of the library, and I have composition. I can easily add new computations on top to get what I want. There's one issue here is that when I run this code, I have ugly side effects. I mean, that thing is going to run right away. There's no IO monad or whatever. So one thing we need to do is to run this into the IO monad. I don't want the side effects to be right away in my program. So in order to do that, you can take a pure fold and transform it into a monadic fold using the into method. So the into method is going to transform a fold going in ID, basically with no side effects, into a fold into IO using side effects. And as a result, when you call run, it doesn't run anything, just returns an IO value with your results. So that's nice. And this works because there is a so-called natural transformation. That's just basically saying that there's a way to transform any value in ID into a value in IO. And that's a pretty simple one. Don't have to do much to do that. But even better, if you use something which we'll see later, which is safety of IO, you can go into safety of IO. And in that case, when you run this thing, the resource will be closed at the end. So the file will be closed automatically because you're running in a safe monad, and we'll have a look at that. So that's even better. Okay, so now we've seen how to reuse stuff, to compose folds, and to read from a file into and having some kind of side effects just because we're reading. But in the previous examples that we had about the financial library and stuff, you also want to write back results, right? And Many times we just read data from a file, do some transformations, and then write back to another file. So to do that, we need some sinks. We need to be able to sync data. So how does it look like? You have this type sync in Origami, which is just an alias for fold with IO as a monad, and just returning unit. It doesn't return anything, so that's a sync. There's no end value which you can expect from it. And there's a method called blah, 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 file UTF-8 line sync, which is allow you to dump strings into each line. So how do I use this? I'm using contramap. That means I'm expecting ints, and those ints are going to be transformed to strings, and the strings, because that's a sync of strings, they are going to be written to a file. And if I run this thing on the list, I will have 1, 2, 3 being written to my file. So that's a way to do fancy I/O with folds. But that's not generally how you would use this. And to see how we can use it, let's see a more complex example using scalaz-stream. So this is what I want to do. I have some data being streamed. Those are strings like that. And what I want is just count the number of letters and get the end results, right? So my initial state is 0. And then once I've seen fold, my new state is 5. When I've seen R, my new state is 8. And when I've seen great, my end result is 13. So I want 13 to be produced. But as we've seen together, that's pretty easy to do. What I want additionally is to output intermediate results to a file. So in particular, I want to output my state, and I want to output the current element to a file. So how can I do that? How can I, at the same time, do some running computations and also output things to a sink? Let's have a look. So I'm creating a list process. So that's a process just created out of a simple list. So that's scalaz-stream. This is my fold doing summing the size of each element, right? So there's the type signature is a bit fancy, but it's just the plus fold, and it's being adapted to take some strings and return the size of each string. Then I need a sync. And there's a method to transform. So there are sinks in scalaz-stream. So you can reuse. So this is a scalaz-stream, this thing here. But there's a method to transform a scalaz-stream sync into an origami sync. So that's called FromSync. And this sync here is going to accept only arrays of bytes. So I need to find a way, because the elements I will have at some stage are just ints and string. I need to find a way to transform those ints and strings into arrays of bytes, which are being used by the scalaz-stream sync. And so I need this transformation here. I need to go from the current state, the current element, and this is what I want to write into my file. Eventually, my final fold is going to be something like that. That's the fold doing simply the summing each line, returning an int eventually. And I'm going to observe what's going on as this thing is folding using this sync. So this strange looking operator here is actually observe with state. And we need quite a few of them, because when you observe what's going on as your streaming element, you can either observe the current element, you can observe the current state, you can observe the current element and the current state, you can observe the current element and the next state, or just the next state. And then you have all those different ugly-looking operators, and that's crazy. I know you don't have to use them. You can use the nicely looking methods, which are more descriptive, right? But this is how you observe what's going on inside your stream. Okay, so I mean, I think that answers a variety of use cases where you just read from a file or read from a data source, do some computations, and output the results to another data source, or data sync in that case. The next thing and the last thing we need to cover now is how you can do those things safely and have resources being closed when you need it. So in Origami, there's something called safety, and safety is a monad transformer. It takes an existing monad and adds some capabilities into it. And let's have a look what that means. So let's say I have a method to read some lines from a file, right? So it's returning in the list of the lines in I/O. Don't care how it's done. And so this is my I/O monad. But I would like this thing to be safe. That means I would like, when this is executed, I would like to make sure that eventually my source is being closed. How do you do this? You use the finally method, and it takes an I/O value, and it's going to add one more action at the end, one more I/O action. So when you execute this read method, it's going to read the lines, and whatever happens, even if there's an exception being thrown in the meantime, it will trigger this finalizer here. So that makes it safe. So that makes this thing, this safety of I/O, a safe method. So you can run this safely. So if I just call run, I will get an I/O value, and I will have the finalizer being called. But there's also another method which is interesting, which is called attempt run. And this one is going to return more information, because now we have more information about what can happen. When you run your action, you can either get a result, everything is fine, but you can also get an exception, because if your computation goes wrong. And at the same time, whether you got a normal value or an exception, you have to run the finalizers. And that can go wrong as well. So if that goes wrong, you will know it, and you will have an option telling you if there was any issue with the finalizers. So that's very nice. That means that you can take a monad like I/O or scalaz task and add one more capability, which is just having a list of finalizers, which are going to be executed finally after you've run your main action. Okay, wrap up. So we've seen how we can encapsulate computations we want to do on streaming elements like average, sum, whatever, as folds with an initial state, a fold method, and a final state. And we can reuse them. So we can just code them once independently from any kind of streaming library. And your streaming library can just be a Scala iterator. That will also work. And we can reuse them across projects. And we can also reuse them in testing. That means that if you're developing stuff for Akka-stream, for example, you can just test your stuff without having to trigger an Akka-stream. A simple list producing elements will be as useful. We have composition, so we have ways to create folds out of simpler folds and make sure that they run in one pass over the stream, which is also important. We can have performance, because I don't have to choose between, the issue I had at the beginning and having to choose between scalaz-stream being nice and functional and composable, nice, but not very performant, and having to use an iterator and a for loop, which was fast, but composition was not so great. Now I can decide to use just an iterator in that case, just reuse all my code. And eventually we have safety. So that's pretty cool. But now I sold everything as the greatest thing on earth. There's a disclaimer. It's not. I think it could be better. There are some issues. First of all, it's not battle tested at all. So I've used it on toy examples. I have a branch of Specs2 that's actually using it, but it's not being made into master. So I expect issues to come up, right? The other thing is implicits. There are lots of different implicits here to make sure that things are foldable and you have the right instances being found in the right place, and it's all in different traits, and you have to use different imports depending on the kind of monad you're using, if you're using I/O or you're using task or using whatever. And that can be a bit tricky. I don't know how to make this better if you have some ideas, but there's a section in the user guide just dedicated to implicits, so that you know where to find implicits. you have basically the same problem when you're using ScalaZ in general. And if you don't want to go import scalaz underscore, comma, scalaz underscore, it's not always so easy to find where are the right implicits to use and how to import them. So implicit is a problem. Breakouts could be modeled differently, and maybe I need to have a discussion with Arnold about that and how to make this better. And the last thing is how the fold operation has been modeled as a pure operation. So the signature is just S, T to S. But if you have a look at the fold L library in Haskell and ECMAT's library, this operation in their libraries are actually monadic. So the modeling is a bit different. I'm not quite sure what's the best way to do it and what are the real drawbacks and advantages of doing that. Because the way I did it, you can also have your state being monadic. So your type S can also be a monad of something. And in that case, you are still in monad land if you want to for your fold. So maybe it's just different ways to skin the same cat. I don't know. And that's my favorite. So if I use IntelliJ for this project, which is not very big, sometimes, not all the time, but sometimes the memory consumption increases, and then poof, blows up. So I have no idea why. And as of today, no one has no idea why. So that, basically IntelliJ is useless, and that's interesting. So I did some references. There's a bit of literature and blog posts which are really, really interesting on the subject. So if you want to go to dive deep into the subject, and Arnold, you're on the references. Good, yes, as you should be. And that's it. Oh, yeah, and the code is here. Yeah, good.
I've got a quick question.
Yeah.
You show composition for folds. What about foldables? Can you compose two foldables of the same type?
Actually, I was thinking about that when we talked about correlation, because basically you have two streams coming in. I think that's the responsibility of the underlying foldable to do that. So you have some merge primitives in scalaz-stream, for example. So I think that's not really in the scope of this library.
Okay, so they have great problems with finalizers and how to, like where to put finalizers, and if you attach a finalizer to a composed foldable, or we'll use your terminology, and the first one completes early, how do you make sure the second one has its finalizer completes, because it never got started? So does it make sense, etc.? So
I know.
Yeah, it's really complicated.
I know.
Yeah.
No,
yeah, fair enough.
I don't have. I think that's
just
outside of the scope.
Yeah. Valid.
Yeah.
Cool. All right. Who is next? Mark.
I've got a few questions, but maybe I'll get the microphone a second time. So the first question was, did you have sequential composition of folds? So if one finishes early and breaks out, can then another one pick up with the remaining results and add on?
No.
That would be quite useful.
Yes. No. I'm actually looking for use cases. I never had this need before. Yeah. Okay.
Second question was, like, you've got this zip. So maybe this is just a minor annoyance, but if you zip more than two things, you're going to have a problem of parenthesization and some languages, I think, like OCaml, they just avoid this at the language level of just say all parenthesizations are equal, and which is great.
Yeah. But, I'm kind of thinking that you should have some shapeless trickery at this level. You just need to flatten tuples, right? And there must be a shapeless method somewhere to flatten any kind of tuple when you need it.
Maybe we can talk after that. I've tried this with shapeless, and there is an example in the shapeless source code that does this, and it works. Until your example is more than 5 or 6 long, and then it just stops working and it doesn't flatten. It's the identity function without throwing an error. And I I asked Miles, and it's because there's an implicit blow up inside the compiler, and it silently quenches that computation.
Okay, that's good to know.
I was hoping you had a good solution, but
no. I was going to go the same route. So okay, interesting.
I'm hogging the microphone, but I had a third question, which was sorry. Iterators started as, well, let's have a fold. We have folds in the language, so let's reify it and make a class out of it. Now let's add pushback and things, and then people worked out iterators weren't so good, and they went to pipes and conduit, and scalaz-streams came out of that. Kind of seemed like in adding back reified folds, it seems we've kind of gone full circle. And I guess my question is, why isn't this already built into scalaz, or is it, instead of a library, is it maybe something that's missing there?
Well, the thing that gives you is the abstraction from the underlying library. So you can use it you can reuse it with another streaming library. If you, for your use case, Akka-stream is better. I have a very small example using Akka-stream in the project, and seems to be working. Yeah.
Maybe it's one of the examples we have a weaker abstraction, doesn't cover all the power.
Yes.
You might have.
Exactly. It's just for folding. Yeah.
No flow control or. Push.
No, the rest is really the responsibility of the streaming library. Yeah.
So your zip operator looks like the applicative operator.
Yes.
But also your problem with flattening multiple zips is pretty much applicable to using applicable. So can you not just make it applicable and then have whatever the hell you want to use apply on?
Actually, there is an applicative instance for fold. So you can reuse the scalaz machinery to... I'm just not sure all the implicits line up, and it's more a problem of Scala implicits being found in that case. But yeah, this thing is actually an instance. So you have, a fold is an applicative. It's a profunctor. It's also comonad. It's not quite a category. It's a category if your monad instance is monad plus, because you don't have a default element for running nothing. Yeah. So yeah, I tried to implement as many instances as I could.
Yeah, sure.
So maybe you can. I didn't try to reuse the strange, scalaz operator to concatenate different zips.
And Macaulay Culkin.
Macaulay Culkin. That's how
You got to use Macaulay.
Oh, okay. Yes.
Okay. Any more? All right. Fantastic.
Okay.
Thank you, Eric.